Next concept we will be studying is the X-bar chart when process standard deviations available. Organizations may choose to follow different set of standards. Organization may not have to follow 3 Sigma standard as their own standard. In this situation, when organization really know their process standard deviation, organization may use information to that information about process standard deviation to construct upper control limit and lower control limit. Organization may choose different set of standards. For example, 2 Sigma standard is about 4.5% defect per or about 45,600 defects per million. 4 Sigma is about 63 defects per million. 6 Sigma is about 0.002 defects per million, or about 2 per billion. In order to construct upper and lower control limit, we will use X bar plus Z sigma X. Sigma X stands for sample standard deviation, which equivalent to standard deviation of the process divided by square root of the sample size. We will use sample 7, Sunnydale, as an example. It's also a good way to also discuss about type 1 error. To use free form of standard to identify upper and lower control limit for X-bar chart, we call this an alternate form. Okay, an alternate form. Okay, an alternate form. Just wanted to review on. Okay, you guys can also go back to the book. An alternate form explain the relationship between the standard deviation of a sample and standard deviation of a process. Standard deviation of a process is larger than standard deviation of sample. Standard deviation of sample is equivalent to standard deviation of sample. Standard deviation of samples equal standard deviation of process divided by square root n. This Sunnydale's bank is a good example of the alternate form. The process has standard deviation of 1.5. Sample size is 6 customers. And organization would like to adopt type 1 error 5% as a standard. In this example, we will convert type 1 error 5% into a z value, which equivalent to 1.96. So in this example, to explain how to convert type 1 error 5%, type 1 error 5% means 5% will be accepted for a poor quality, or about 95% will be accepted as a good quality. Out of 5% poor quality, about 2.5 will be higher than upper control limit. about 2.5% will be lower than 2.5%, lower than lower control limit. Okay, we will use appendix 1 to find out the z value. With 2.5% upper and lower, we will take 1 stand for 100%, subtract 0.025, which equal 0.975. Which 0.975, you use that to find z value in appendix A, which equal 1.96. Okay, so the upper and lower control is about 6.2 and 3.8. There are 2 occasions that resampled. One is 3.7 and one is 3.68. The question asks, is the process in control? Okay, it seems to be that the 2 successive additional samples that collected is lower than lower control limit. Therefore, we can summarize that there is assignable cause of variation. Therefore, process improvements must proceed. Okay, so that's the end of example number 7. Okay, next we are going to proceed to the control limit for attribute. For control limit for attribute, why we call control limit for attribute? We call control limit for attribute because the outcome of the process binomial pattern. If the outcome of the process can either be yes or no, good or bad, only 2 possible outcomes, we call this binomial distribution. The control chart for attribute can be used to detect the variation for binomial distribution situation. Therefore, control chart for attribute can be used for 3 forms, meaning that control chart for proportion may accept any type of standard as z value. So the upper control limit for P is P bar plus z sigma P. Lower control limit is P bar minus z sigma P. Okay. The P stands for proportion defective. Okay. This example show you about hometown bank. Each week, a random sample of 2,500 deposits is taken. Okay, the following are the outcome. So the company select 12 samples, each 2,500 of the sample size, and then correct the wrong account number of each occasion. Total wrong account number is 147. So to find P bar, you take 147 divided by 12 samples times 2,500 each, you get 0.0049. Then you proceed to find sigma P and then substitute with the standard, which is 3 sigma. You're gonna find upper and lower control. Then use the P to plot with upper and lower. P bar can be used as the center. As you can see from this figure that the process is out of control. Okay, with this example, we are going to use example number 6. Draw a chart. Example 8, not 6. Okay, for this example, you have a sample size of 100 and you have about 15 samples. So first you will find out proportion P, which you take number of error divided by sample size. Okay, after that, with this P, then you have to, you're gonna have to find P bar. You're gonna use an average of P over here. So that we call P bar. Okay, all P bar can be found by using another approach. Okay, P bar can also use another approach. Okay, another way to find P bar is to use sum of the error divided by number of observations times sample size of each. Okay, so don't forget to also parentheses. Okay, you can see that's the same amount. Okay, you either use total observation divided by number of samples times sample size, or you can just average P bar. Okay, and next step is to find sigma P. Okay, sigma P or standard deviation of P can be found by using sigma P equal square root sqrt of P bar times in parentheses of 1 minus P bar divided by sample size 100. Close parentheses. Okay, about 0.0172. Okay, now next we're gonna construct in this example. Okay, in this example, we are interested to find out we use 95% confidence interval, or about 5% type 1 error, or equivalent to 1.96 standard deviation. So that's z value equal 1.96. Okay, so we're going to start upper control limit P, lower control limit P, and then center line P and P. Upper control limit P equal P bar function 4, don't forget, plus Z function 4 times sigma P function 4. Lower control limit P equal P bar function 4 minus Z times sigma P. Okay, and for the center line is P bar function 4, and also P is the P on left. Okay, pay attention to this. If the outcome is negative like this, we must adjust the 0 because the minimum error that organization may have is 0 error. So we will adjust that to 0. Okay, once we have that, then we make sure that you all that change to 0. Okay, now okay, so we're gonna draw a control chart. You can see that there are 2 occasion process is out of control. Okay, so the process is out of control. So I hope students use examples available on the package that I give it to you to practice some more on question 9 and question 10. Okay, next we are going to also go to another chart we call a C chart. Okay, C chart and P chart are different from each other. C chart can be used for the situation when you have only one sample size. Okay, for example, when you count how many errors that you make on one piece of paper, one piece of paper is sample size equal 1. Number of error is the count that you have. In that case, C chart is appropriate. P chart, on the other hand, P chart sample size is more than 1. Okay, for example, if you have to identify a bad apple from 1 bushel of 100, when you identify there is 3 bad apples out of 100, P is about 0.03. So in this occasion, number of samples is more than 1. We use proportion chart. On the C chart, upper control limit C equals C bar plus Z square root C bar. Lower control limit is C bar minus C square root C bar. So we're going to use example number 11 to complete this. On 11, okay, we count how many dimples we make on a tabletop fiberglass. So sample size and always equal 1 unit. One, in this case, fiber glass top. Okay, so first we're gonna find out C bar by average all the dimple. We call this C bar. Okay, so upper control, and in this example, sigma or Z equal 3 sigma. So we can use upper control limit C, lower control limit C, center line C, and C count. Upper control limit C equal C bar, okay, plus function 4 type z function 4, don't forget plus z function 4 times square root sqrt square root c bar function 4 close. Okay. Lower control limit will be c bar function 4 minus z function 4 times square root c bar function 4. Okay. When every time there's something negative like that, okay, as you know, there is the minimum number of dimple will be 0, so 0 can be adjusted to 0. Okay, and control limit, center limit will be c bar, and c will be count of the dimple. Okay, so with these 4 we can insert the chart. Okay, and put in C chart. Okay, and we call process is in control. Okay, don't forget to save it to use it further. Okay, so we finished all of the control chart. I hope you guys are comfortable using P chart. Next stage is also one tool that Six Sigma can provide in addition to a control chart. We call this process capability. Process capability refers to the ability of a process to meet the desired specification for the product and service. Desired specifications are often expressed as a nominal value and a tolerance. Okay. For example, the nominal value in this picture is 25. The tolerance value is 5. If you put 25 plus minus 5, 30 will become upper specification and 20 will become lower specification. If the process produces products that has an outcome within this upper and lower specification, we call the process is capable of making the specification or meeting the specification. On the other hand, if the process has an outcome that go beyond upper or lower specification, we can call the process is not capable. Whether or not the process is capable, you must compare with standard. Okay, in the box on the left, it's on page 169 also. I'm sorry, on page 179. Okay, on page 179. Okay, when you compare with 3 Sigma standard, the critical value or CV you are going to compare is 1. 4 Sigma standard is 1.33, 5 Sigma standard 1.67, and 6 Sigma standard is 2. Where this number come from is the number that compare between 3 sigma and the standard. Okay? If 6 sigma means 3 sigma divided by 6 is, which means it means you achieve 6 sigma compared to industrial standard of 3. 6 divided by 3 will be 2. So the number is equivalent to what you can achieve compared to industrial standard. Okay, there are 2 indexes that you must use to assess your process capability. The first one we call CPK, which is mean of x bar minus lower divided by 3 sigma, comma upper minus x bar divided by 3 sigma. Process capability is a measure to use to express how well the process is centered and whether or not the variability is acceptable. Another one we call CPK, or process capability ratio, which is upper divided by lower, upper minus lower divided by 6 sigma. Okay, now look at example. This example, okay, the process standard deviation is 1.35. The process has average of 26.2. Process has nominal value of 25 with tolerance of 5. Upper is 30, lower is 20. You want to know whether or not the process is capable of meeting 4 sigma standard. Remember, 4 sigma standard is 1.67 CV. Okay, so first you find out the CPK. Okay, you can see that both CPK you find 1.53 and 0.594. We take the minimum one, 0.94. 0.94 is lower than 1.33. I think I told you 1.67 is not right. Okay, the CV for 4 sigma standard is 1.33, meaning that the process is not centered, it's not capable of meeting the process. For the CPK is used to assess process variability. Upper minus lower divided by 6 sigma is 1.23. Compared to 4 sigma standard, the process also not capable, meaning that the process have high variability outcome. Okay, with that we are going to use example